All right, physics reaction video number 26. So this looks like it's an hour-long recording, and it looks like it was an entire class, but I just fast-forwarded until I saw some handwriting, and it looks like that some handwriting starts about here. So we'll get it started.
In the next, there's this sled that's on an inclined plane, and I mean the first thing you've always got to do is decide what kind of forces act on it. You have F sub g, and then there is a normal force which acts in this direction, and then there's also friction, and that's the only other force. So although the problem prompts you to do some kind of kinematics first, this is a good description of the free body diagram.
So I like that, right? So the problem just kind of apparently got to the guts of it and said, hey, let's, I don't know, maybe figure out how fast it's going or something. And he's like, look, free body diagram's never going to hurt, so let's go ahead and do it. He draws remarkably straight lines that are at exactly the right angle. I mean, this really does look straight down. This looks basically at 90 degrees compared to the hill, so that's pretty cool. And he says, and the only other force we have is friction. So good setup so far. I don't know what even before I rewound a little bit there, it doesn't look like there's a description of the problem anywhere that is on his screen. Obviously, his students have access to it. So I'm not 100% sure what this problem is asking, but we'll keep on trucking here.
It's critical that you only include forces that actually act on the object, and the force due to gravity is present. The normal force is the force that the surface pushes up on the sled with, and then there's friction. That is it. You don't show any other forces besides those forces. In part A, you want to know like what time it takes to go 21 meters down the slope. And the problem says that it travels at a constant speed of 2.4 meters per second. So you have a velocity of 2.4 meters per second, and then you have a time of, here, let's see. Oh, you have a distance. So
it's all involved. We'll figure out what to do here.
There's a distance of 21 meters. Just from the definition of velocity is displacement over time. So the time it takes to get down there would be the distance divided by the velocity. You're going 21 meters at a speed of 2.4 meters per second. That's 8.75 seconds. Because there's only two significant figures given in the values, 8.8 seconds would be like an appropriate amount of time.
All right, sorry, can't help it. I'm not a fan of significant figures, but certainly, what he's doing there seems good. Of course, the true rules of significant figures says that this is a perfect number unless there's a decimal point there, but whatever. Anyways, we've got 2 digits of precision up here. Put in the comments below why you think you can ask me about my significant figures. Hang up if you'd like. All right, so a couple of really interesting things. So here we have this free body diagram with forces all over the place, and you think, okay, we're going to have accelerations and everything. And part A says, oh, it's at a constant velocity. And so already you're getting a hint at what the frictional force must be, right? We're at some sort of terminal velocity here. The other thing... Oh, yeah, so 21 meters, it's a decently long pass in football or in soccer, taking about 8.8 seconds to get there. That seems slow. So, yeah, 2.4 meters per second. I feel like I could walk that fast. 6 miles an hour, yeah. Okay, so this is not a fun sled ride, I don't think.
It'd be okay to leave the 8.75 for further parts of the problem.
Of course it would.
Make sure I got my participant list stuff okay. So that's A, and part B is the free body diagram.
He jumped ahead.
What's the friction force as it slides down the slope?
Well,
here's the thing. If the problem says that the object is traveling at a constant speed, that's the real key. If it has a constant speed, then there must be no net force.
So this is really interesting, right? So when he first said what part A had to do, he didn't really harp on the fact that it was a constant speed. He just wanted them to realize that part A was easy, right? Part A, good Lord. I mean, it's just this one fundamental definition of velocity that he's having them explore. And he waited until there was a question that really needed this stuff, part B. And now he's like, oh, did you realize, you remember back there how easy part A was? It was a constant velocity. Wow, we can do this problem now. So that's really intriguing because I think that the mistake I think I would have made is I would have made a big deal about it up here, which is really not needed until part B. So it's interesting too that he drew the free body diagram that got us thinking about forces and accelerations, but doesn't have to use them until part B. So there's some interesting questions here about the order and the emphasis. Like, when should you really say, hey, did you notice that? It was a constant velocity. He really just kind of churned through this, and now he's really fixating on that. So I think that's interesting.
A net force of 0 doesn't necessarily mean that the object isn't moving. It only means the object is not accelerating. So, although this is the only free body diagram you want to show in the solution, the force due to gravity has two components. There's a force that acts perpendicular to the plane and a force that acts parallel to the plane.
Man, he's good at that.
Perpendicular to the plane is equal to F sub g cos theta, and the one that's parallel to the plane is F sub g sine theta. And in order for the object to...
So it's interesting, right? There's no theta on the diagram, and so we don't know how the problem, the book, or the quiz, or whatever had theta defined. But I want to talk about this for a little bit because I believe, here's how I'll do it. I'll just model for you how I do it for my students. Like, I wonder which angle is theta, and the only two choices are this compared to horizontal and this compared to vertical, right? So it's either this is theta or this is theta, right? And often my students get really confused, like, when should I use cosine, when should I use sine? So let's pretend it's this one. Let's pretend this is theta over here. Well, cosine, let's go with sine, my favorite first. Sine gets smaller when the angle gets smaller, right? So if I were to bring this slant down, so that theta, let's assume this is theta. If I were to bring this slant down, theta would get smaller, so I would expect this to get smaller. Well, sure enough, if there'd be way less force down the hill if theta gets smaller. So yep, this is going to be sine, this is going to be cosine, so this is angle theta. If this were theta, and we say, oh, well, what happens if theta gets smaller? The only way to make this angle smaller is to have this go more vertical. Well, if this goes more vertical, this leg of the triangle gets longer, so this would be cosine. So if in fact this were theta, this would be cosine and this would be sine. So basically what I say to my students is just sort of mentally imagine the angle getting bigger or smaller, whichever you like, and look at the sine guy and take a look to see if it gets bigger or smaller. And or I guess before you even label who's sine, figure out which leg of the triangle gets bigger or smaller when you do that with theta, and that'll help you know who's sine and who's cosine. The other thing is, I'm very sure that every single problem he's ever done with this problem probably has had theta be here, but also in the book or wherever this came from, I'm sure it was labeled.
Travel at a constant speed, the acceleration must be 0, which means the net force is 0. And if the net force is 0, there's two conditions that have to be met. The sum of the forces in the x direction have to be 0, and the sum of the forces in the y direction has to be 0. In the x direction, which is the direction parallel to the plane, what's got to be true is that the friction force is equal to F sub g sine theta. And what must be true in the y direction is that F sub g cosine theta is equal to the normal force. So those forces in the x and y directions, they have to be balanced out. So the problem is, what's the friction force? Well, it might be this, or the other definition of friction force is equal to the coefficient of friction times the normal force. You don't know what the coefficient of friction is. So it's not reasonable to calculate the friction force as being equal to the coefficient of friction times the normal force. But what you do know is that the friction force has got to equal F sub g sine theta. F sub g is mg, so you got 25 kilograms times.
So this is really interesting, right? Because you could do it this way if we knew what mu was. And he says, we don't know what mu is, so we're going to have to do it this other way. But of course, as soon as you have this, then you can figure out what mu is, right? So So you could imagine a part D to this problem that has mu get figured out. But I love how careful he's being, right? Because students can really get confused. What is friction? A lot of students might think, oh, mu is just friction. No, it's mu times the normal force. And I think that indicating to them, they say, look, we can't go this route because we don't know what mu is. So let's go this route. It's really giving them sort of some reassurance like, hey, we can pull this off. I think later to say, okay, let's calculate what mu is can feel a little bit strange. Like, what the heck do we need to know mu for? We already know the whole frictional force. Mu is just like a step towards calculating the frictional force. So you really have to sort of couch that stuff. I don't know if there's a part D to this problem, but I really liked how he said, look, a couple of ways to do it. We're going to do this one because we have everything we need.
9.8 meter per second squared. They get you F sub g times the sine of the angle. And you know that this angle of incline 15 degrees here, that's the same as this angle up here.
Love
15 degrees. That's the 15 degrees that's in the sine of the angle. Where the coefficient of friction plays in is the only formula at all that has coefficient of friction is this idea that friction force is equal to coefficient of friction times the normal force. So every time you need to calculate a coefficient of friction, it's always the ratio of the friction force to the normal force. And the friction force is the same as this F sub g sine theta.
So the way he's couched this, I love it. He's doing great stuff. But there's a really funny thing that students can do sometimes in this situation. They say, okay, oh, well, let's see. Here's my fundamental definition of mu. Oh, so I can calculate this. Oh, sweet. I can just grab this and throw it right here. And all you're left with is mu equals mu. My buddy in grad school and I used to say, oh, we've proved 0 equals 0 again. And so, right, this is the problem, right? That there's so many things you can throw at this that some of them are dead ends because proving that mu equals mu is kind of boring. So I really like that, he's got it set up and now he's got to go over here and say, well, what can we do? My guess is he's going to grab this one instead of grabbing this one. Let's see what happens.
Theta. So that's like what you calculated in part C. And the normal force, which is the force that acts perpendicular to the surface and up, that's equal to F sub g cosine theta. So you have F sub g cosine theta in the denominator. And I did this proof for you as a derivation in class, and it has to do with that concept of limiting angle of repose, which is both the angle at which an object will begin to slide based upon its coefficient of static friction.
Mm-hmm.
But in this case, that coefficient of friction and angle relationship, so you can write it one of two ways. Mu sub s, well, as this derivation, the F sub g's cancel out.
Love it.
And sine theta over cos theta is equal to tangent theta.
Yeah,
so there's two ways to think about that, limiting.
Before he goes on, I really love what he's about to talk about here, but before he goes on, this notion that the FGs cancel and that you just get the tangent theta is cool, but you're definitely going to have a lot of students who are going to say, oh, okay, I need a force of friction. I'm just going to grab my answer from part A and put a numeric thing there. And then I need the normal force. Oh, okay, let me just clunk this in my calculator, and they'll put it down there. And they'll get the right numeric answer. But this idea of putting it down algebraically, and especially pointing out that the force of gravity cancels right away, apparently the mass doesn't matter, right? The mass doesn't matter when calculating mu. Now, of course, the mass matters to determine what the strength of the frictional force is, but that's kind of the slick thing about mu. It's not friction. It's like this thing about materials. Now, I don't care how much of that material you have. If you put this material on that material, mu is going to be this. And we can see that here because the masses, and by the way, gravity cancels too. So this apparently would work on the moon, right? That's super cool. What he's about to say, this idea of, I think what he's going to say is what I would call terminal velocity. That angle would still create terminal velocity on the moon. Wait a second. Let me think. Yeah, it would still. So that's really cool. Let's see what he's doing over here. He's talking about how static friction often is like you raise the ramp, until it starts to slide, and that's when you kind of break that frictional bond. But that's not what we're doing here. We're doing constant velocity terminal velocity if this was air resistance. So I think that's a really interesting way to think about it.
Angle of repose. If it's a coefficient of static friction is equal to the tangent of the angle, this is the angle at which the object begins to slide. And that angle is going to have to be larger than the angle that's necessary to keep the object sliding at a constant speed.
Yeah.
So when it's mu sub k, it's also the tangent of the angle, but this is the angle for constant speed.
That's so cool. Those two angles aren't the same. So what he's saying is that if you raise to this angle, so it's just sitting there flat and you start, and it starts to slide. If you then lock that angle down, it's actually going to accelerate, and you'd have to back it back down a little bit to get it to go at a constant speed. So the thetas are smaller. Luckily, tangent, like sine, unlike stupid cosine, gets smaller when the angle gets smaller, right? So it's well, at least at the beginning for sine. And so this I thought was a really, really great explanation of getting confused by an equation they might find in the book. Wait a minute, how can the coefficient of static friction be the same equation as the coefficient of kinetic friction? He's saying, well, this is something you can do in the lab, but you're looking for different things. You're looking for object begins to slide versus constant speed.
In the case of this problem, it would be like there's some angle here, theta, to make it just begin to slide. All right, theta sub s, but the angle to make it slide at a constant speed is going to be a smaller angle.
Cool.
All right, theta sub k. Hopefully you can see that I made this one like a little bit lower. And if the angle theta is smaller, then the coefficient of friction is smaller. So theta k is less than theta s, and that's because mu sub k is going to be less than mu sub s.
So I think that this is easy to do in the lab. That just raise it till it starts moving, right? And you could go raise it really, really slowly and watch it, and then there's this moment. Oh, it's moving! Hey, it's moving! So that's your angle. This one is hard. I mean, constant velocity is hard. And by the way, if these two angles are close to each other, you might sort of wobble it, and it'll come to a stop. And then, you got to break it again, and then it'll come to a stop. So I think that it's really interesting to think about what's easier in the lab, too. This one's way easier. I think this would be a tough... I'm trying to think how hard that lab would be. I think that constant velocity is really, really, really tough to do. I guess you just do it over and over again. You could break it, have it be broken, and then you could lower it to some lesser angle and watch it. And then, does it come to a stop? Does it speed up? Oh, do that over and over again. That's how you can get this this kinetic angle. But this one I think is pretty easy to do. Hey, this I thought was really, really cool. The things that I liked about it was his fantastic ability to draw angles perpendicular to each other. I think that the 15 is labeled here now, but it's really interesting to think about. One of the big confusions that students get is, where does cosine go? Where does the sine go? I really thought it was interesting that he didn't really harp on the fact that the velocity was constant while doing part A, but he came back to part B and C, and it's like, whoa, hang on a second, there's something really interesting going on here. And I also really, really loved the algebraic work that he did here, and then this discussion that he had, because this can be really confusing to the students, that the equation looks exactly the same, but it's because the angle is measuring two different things. All right, everybody, thanks so much. Have a great day, and remember, physics teachers are awesome.